There's a growing debate today around the claim that a quantum computer activated in the year 2035 could pose a serious threat even to data from 10 years earlier, meaning our present time. When I first heard it, I thought it sounded like the beginning of an exciting science fiction story. If this really were science fiction, then certain questions naturally come to mind. Are quantum computers going to break the laws of time and send messages into the past? You can actually find hundreds of videos on the internet that suggest this idea. Let's assume that's impossible. Then how about another popular claim that quantum computers will somehow use parallel universes to pose a threat? Neither of those is true. The reality goes far beyond that. This issue is not abstract or theoretical. It's much more concrete and dangerously close. There is no science fiction here, only science. The claim is this: within the next 10 years, quantum computers will reach the power to break nearly all the encryption systems used today. But immediately after, experts add, if encryption systems are upgraded in time to be quantum resistant, this threat can be avoided. It's a serious matter, so much so that the United States has already taken action. The National Institute of Standards and Technology, known as NIST, officially established post-quantum cryptographic standards in 2024. This transition won't happen overnight. Every public institution and private company is required to gradually update their systems to meet the new standards. In fact, the process is now law. The full transition must be completed by 2030, and compliance with these standards will become legally mandatory in 2035. But here's the real point of confusion. How can a quantum computer build in 2035 possibly affect the year 2025? At first glance, this seems to violate every known rule of causality. But the issue is actually more nuanced. Let's consider a scenario. Suppose that in 2030, a quantum computer is developed that can break modern encryption systems based on the principle of factoring large prime numbers. And imagine this powerful machine ends up in the hands of malicious actors. That same year, some institutions that failed to update their systems are breached, and their encrypted data is exposed. But why would this affect the past? How could an event in 2030 possibly have consequences for information created in 2025? Well, it's not as mysterious as it sounds. We don't need time travel. We don't need alternate universes. Everything happens right here in our own universe, under normal rules of time and causality. To make sense of this, we need to briefly understand today's RSA encryption technology. If we ignore other layers of security, a basic requirement for two machines to communicate securely is a public key. This public key is visible to everyone. But there's also a private key, and unless both are known, the encryption cannot be broken. In theory, it is always possible to calculate the private key by using the public key. But in practice, it's nearly impossible, as long as the numbers are large enough. Let's take a very simple example. Imagine publishing 21 as your public key. The private key, which only your recipient knows, is 3 and 7. The message is locked using 21, but can only be unlocked by someone who knows the original prime numbers, 3 and 7. If someone can quickly figure out which two primes multiply to make 21, they can unlock your message. Now replace 21 with a 10,000-digit number. Suddenly, factoring it becomes virtually impossible, not because it's unbreakable in theory, but because it would take classical computers billions or even trillions of years. And that's the whole point. It's not about violating causality. It's about the fact that data encrypted in 2025 might still be sitting on a server somewhere, waiting to be decrypted in 2035. The moment someone gains the power to break that encryption, they gain access to the past. At its core, this is a problem of time. Take a large number with 1,000 digits. Even the world's fastest classical supercomputer wouldn't be able to factor it into two prime numbers in less than 20 billion years. That's the essence of RSA encryption. Its strength lies in the difficulty of factoring massive numbers. But back in 1994, long before quantum computers even existed, physicist Peter Shor developed what would become a groundbreaking algorithm. This algorithm, now known as Shor's algorithm, was designed specifically for a quantum computer, a machine that didn't yet exist. At the time, it was admired by cryptographers and mathematicians, but mostly ignored by the wider scientific community. So, why are quantum computers such a game-changer here? The answer is surprisingly simple. A classical computer breaks down a number by trial and error, checking possibilities one by one. As the number grows, the process becomes like searching for a needle in a haystack. It can take years, or even longer. But a quantum computer works differently. Thanks to the power of superposition and interference, it can explore millions of possibilities at once. Shor's algorithm uses hidden periodic patterns within numbers to efficiently narrow down the correct factors. It's like this: while a classical computer walks a straight path, one step at a time, a quantum computer runs down thousands of paths simultaneously. That's why Shor's algorithm can solve the hard mathematical problem of prime factorization much faster than any classical method. Now you might be thinking, okay, but you still haven't explained how a future event could affect today. Fair point. And that's exactly what we'll explore next. Let's say that in December 2025, a long-standing issue related to plasma stability and fusion energy is finally solved by scientists at the West Fusion Reactor site, a collaborative project involving experts from around the globe. This discovery becomes one of the most valuable pieces of knowledge in human history, representing the potential for unlimited energy during a human lifetime. However, commercializing this system will require the development of new materials, a process expected to take at least 10 years. To protect this critical information, it's stored on a drive secured with one of the most advanced encryption systems available in 2025. The encryption is so robust that no existing technology can break it. But then, one of the researchers, acting with good intentions, copies the data onto a personal drive to work on it from home. While working, he falls under cyber surveillance by unknown parties, and the encrypted data is stolen from his computer. Upon discovering the breach, the scientist quickly performs a rough calculation. As of 2025, the world's most powerful classical supercomputer is El Capitan at Lawrence Livermore National Laboratory in California. This machine has only been able to factor 250-digit, or 829-bit, number. In contrast, the stolen data contains a specially constructed number with 10,000 digits, roughly 33,000 bits. Even El Capitan would need at least 1 trillion years to factor such a number. Given that the universe is only 13.6 billion years old, the data seems practically secure. You might wonder, what if a quantum computer could break the encryption? So far, quantum computers have only successfully factored a 90-bit number. Compared to 33,000 bits, this doesn't seem like a real threat. You feel safe and continue your work. Materials development still has 10 years to go. No quantum or classical computer appears capable of breaking this encryption yet. But things don't go as planned. Just 4 years after the data breach, scientists discover that Majorana particles can be used in quantum computing. By year 5, a 1,400-qubit quantum computer using Majorana particles becomes commercially available. You think, who will buy such a thing? Then, you see it for sale on a platform called TemuX. And that's when real fear sets in. By 2030, the person who stole the data buys this quantum computer from TemuX and cracks the encryption. What happens next with this data is anyone's guess. It's important to note that breaking a 33,000-bit encryption doesn't just require a powerful quantum computer. It also demands an exceptionally stable and robust error correction system, something far beyond what exists today. As of now, such a quantum computer simply doesn't exist. But one day it will. Here's the essence. If highly encrypted data is collected and stored today, it could potentially be decrypted in the future once quantum computers with sufficient power are developed. This is exactly where the idea of quantum computers of the future affecting the present originates. Whether you find that plausible or not is up to you. So what can be done? The most crucial thing is to ensure your data is not stolen, even if it's encrypted. Transitioning to quantum-secure encryption will take years, maybe decades. Until that process is complete, any message sent using today's classical encryption methods could, one day, be deciphered by a quantum machine. Depending on how long you want to keep a secret safe, the time to worry might have already passed. A similar situation happened in the past. When the RSA encryption method was introduced in 1977, it used 512-bit protection. That number increased to 768 bits in the 1990s and to 2048 bits in the 2010s. Today, 4096-bit encryption is not uncommon. But remember, the strongest classical computer has only been able to factor a number of 829 bits. So technically, older 512-bit keys should have already been cracked. And yet, we've never heard of any major breaches involving RSA encrypted secrets from 1977. If you enjoyed this topic, don't forget to subscribe to our science channel and like this video. Your support helps us reach more people. See you in the next episode.